Hello everyone and welcome to Lecture Today. Today we'll be talking about various applications of the double integral. And we'll see that these applications actually extend directly to the triple integral as well when we get to that. But we're going to focus on several different applications in electrical engineering and in mechanical engineering. So specifically related to physics and electrodynamics. Specifically, we'll talk about what's called how to calculate the total mass of a region given a mass density function. And related to that, but in a completely different area, is the total charge, total electric charge of a region. Given some mass or a charge density function. And for both of these two applications, the formulas that we're going to get are going to be very, very similar to one another, almost the same thing. It just, the interpretation of the density function is going to be different. This is all in 2D, so the region R here is in 2D, because we're dealing with a double integral. So we'll then move on to what's called the center of mass. Of a 2D region R. And just like we have, also have the concept of total charge with the charge density as well as mass density, we can talk about the center of charge. In some sense, the formulas that we derive are going to go together very closely. So these two are going to be very similar to one another. These two are going to be very similar to one another. And related to the center of mass formula, the center of charge formula, we'll have, we can find a formula for what's called the centroid, or the geometric center of a region R. Basically, this is going to be a simplified formula from that we can obtain directly from our formula for the center of mass and for the center of charge. And the last two applications we'll talk about is what's called the moment of inertia. Of a region R. With a distributed mass density, as well as what's called the moment of the charge distribution. Inside a region R. This is related to what's called possibly the dipole moment. and many other things in electrical engineering. So we'll start by talking about deriving a formula for both the total mass of a region R and then briefly comment about how this formula is going to be very similar to the formula for total charge. So the main idea here is that we're going to think of having, in general, some region in two-dimensional space we'll call that region R. In any region like this in two-dimensional space, we very often can call, and we do call in applications, lamina. And that just means you can think of like a flat plate in 2D. So if we consider all of the points on this lamina, very often we can have what's called a mass density defined, mass density function defined all over that lamina. So the idea is that there may be certain regions, maybe like here and here. You can also even say maybe a third region or however many regions you want to consider, where the mass is very heavily concentrated. There's a lot of mass per unit area. In this case, maybe you're measuring in kilograms per meter squared. But as you move around the plate, maybe there's less and less mass. As you move away from these heavily concentrated regions, until when you get very far away from any of these heavily concentrated regions, maybe the mass density is very, very small. This is one picture that you can kind of think of when you're thinking of a general mass distribution. You have regions of the plate that are very, very highly concentrated, where there's a lot of mass per unit area. And as you move away from those regions, the mass per unit area gets less and less and less. And this is generally the case that's true for most materials. I'd say the majority of materials that you encounter are not all uniform or don't all have the same mass density over the entire material. So the issue here then is that we have to describe this with a multivariable function. So typically for a mass distribution, we say that the mass density function, or the mass per unit area at a point, is a function of x and y. And this is called the mass density function. Similarly, if you have you're dealing with not the application of mass, but you're dealing with the application of charge, you can have a charge density function. Typically in physics, we use the notation sigma for a two-dimensional charge density function. This stands for charge, or electric charge per unit area. This is at the point xy. In general, a mass density function has to be positive or equal to 0 at any point. So rho of xy has to be greater than or equal to 0. But the charge density function can be positive or negative, because you could have positive or negative amount of charge per unit area. That's an important distinction to make right off the bat between these two examples. So sigma of xy is a function that can be either positive or negative. And basically, this density function essentially is you can compute it in general if you know geometrically. You take a very small region. This rho of xy at any point is the amount of mass over the differential area at any given point. And this is important. We'll come back to this idea when we go through the derivation here. So this can be a little bit tricky to visualize at first. So what I've done here is showed a plot of an example density function and started to fill it in with points that are distributed with a density that corresponds to that density function. See that there are 5 peaks of this density function, and gradually as we add more and more points, you're seeing that there are regions where there's a higher mass concentration and a lower mass concentration. This maybe isn't so well to see when you look at just the black points, but if you color the points with their individual mass density at each individual point, you can very clearly see that there are regions of higher mass and lower mass, and figuring out the general properties like center of mass, total mass, and moment of inertia of such a region is in general difficult. For a symmetric region, it's not too bad, but if we kind of go to this new density function, which is a little bit asymmetric and not super nice, you're seeing that this problem becomes a lot more difficult. So we need to go through and investigate what the correct formulas are that give us the correct properties of this region, such as the center of mass, the moments of inertia, the total mass, and so on and so forth, for a general density function. What's incredibly useful to know and to see here is that all of this stuff also applies to total charge, so electric charge into many, many other areas of applications. This also has a lot to do with, and a lot of relationship with modern probability theory, probability and statistics. And it's amazing to me that, it'll always be amazing to me that these two fields of mathematics that seem very separate, mathematical physics and probability and statistics, are actually very, very closely related in how certain things are described. But what we'll see, what we're going to justify in just a second, are the following two formulas. At total mass, the total amount of mass contained in a region R, or in a lamina, is directly equal to what we'll call this M, capital M, just to kind of, for notation. But this is exactly the total accumulation of the mass density function which we directly know how to compute. Its the double integral over the region R of the mass density function. This is saying that if you have a region R and you have a mass distribution of which you know or you can approximate the mass density function, you can calculate the total mass contained in that region just by taking the double integral of that function over the region. And the exact same thing is true if instead of a mass density function you have a charge density function. Total amount of electric charge contained in a region R which we'll call capital Q is directly equal to the double integral or the accumulation of the charge density function over that region R. So we'll see in a second an example of how to apply the total mass formula, and we'll stick with the mass formula, but applying the charge formula is the same exact process. You need a density function and you need a region R, which is a lambda, and you just integrate the density function to determine the total amount of whatever quantity the density function is describing in that region. Before we see the example, though, let's just kind of justify this. We want to always justify our mathematical statements, and we're going to do that using Riemann sums. And the way that we're going to use Riemann sums to do that is, again, we always, when we're using Riemann sums, we have our lambda R. This is our region R. So we know that the Riemann sum process is the process of cutting up our region R into a whole bunch of very small pieces that we call pieces of, a partition. And we take the limit of this process as these pieces get smaller and smaller and smaller. So we have finer and finer cuts in the partition. This is how we defined previously exactly what the double integral is for a function of two variables. So we're taking this limiting process all the way down until these pieces get smaller and smaller and smaller. And if we zoom in on one of these pieces and evaluate it, so we kind of look at what we're doing here. So we have, say this piece corresponds to the ith cut along J and along the x-axis, and the jth cut along the y-axis. This piece has area delta Aij, and we have to have a sample point here as well that we're sampling at. That corresponds to xi star yj star. We have a sample point like that in every single one of these rectangles. So the size here is, the width is delta xi and the height is delta yj. So in the limit, as these rectangles get smaller and smaller and smaller, you'll remember that the approximation, or the Riemann sum approximation for the double integral of the density function is actually going to be the same thing as the sum of an approximation to the sum of the mass, right? The total mass of this object, this lamina r, is going to be approximately equal to the Riemann sum Sn, where Sn is the double sum over all of these rectangles of delta mij, where delta mij is approximately equal to the mass of a rectangle ij, or the ijth rectangle. So if we add up all of those delta mij's, we're approximating the total mass of the region R. It's not exact, but it's an approximation. And the idea here is that in the limit, as these pieces of the partition get smaller and smaller and smaller, this summation gets closer and closer and closer to the actual value of the mass. Well, we know that delta mij for very small values of the rectangle is going to be approximately equal to the density at the sample point multiplied by the area of the ijth rectangle, because the density function at the sample point is approximately equal to the amount of mass contained in the jth rectangle divided by the total area of the jth rectangle. Now this is only, again, approximation, because that the actual density is varying throughout the medium, but for small values of delta x and delta y, we have that this is giving us a very nice approximation for a nice density function. And so what that means is that the total amount of mass of the entire lamina itself is approximately equal to the Riemann sum, we'll call this Sn, which is the sum from, and this is different than this Sn, we'll call this the sum from 1 to n, from j to 1 to n of delta mij, which is approximately the density function at each sample point, so that the density function sampled in each rectangle multiplied by delta aij, which means that the total mass then is equal to the limit of this Sn prime as n goes to infinity, which is exactly the double integral of the density function over the region and there you have it. So this is a very, very nice justification of why this formula should hold and why it does hold in general. So if you want to calculate the total mass or total charge contained in a region, all you have to do is take the double integral of the density function for that region. So let's look at a very specific example to sort of try and see how we would apply this. Let's try and find the total mass contained in the lamina bounded by y equals 0 and y equals 4 times x minus x squared, or a density function that has a minimum value of 2 at the origin and varies quadratically with the distance from the origin. The first thing that you always want to do when you have one of these problems is to make a distinction between the geometric domain and the mass density function. So this, first we'll consider the domain in this lamina, so the actual shape of the lamina. So it turns out that this function, and this should be y right here. Y is equal to 4 times x minus x squared. So the function y equals 4 times x minus x squared goes from 0, x equals 0 to x equals 1. It looks like this. It's a downward opening parabola with a maximum height of 1. And then y equals 0 is just this straight line right here. So this is the geometric lamina, or the region that we're considering finding the total mass of. Not only that, but we have an exact verbal description of the mass density function. So the function that has a minimum value of 2 at the origin, or when x equals 0 and y equals 0, and varies quadratically with distance from the origin, is the following function. This function right here is when x and y equals 0, or you're at the origin, the mass density is 2, and then the level curves of this function are circles. So as you move away from the origin here, you see very clearly that the mass density of this function is increasing as you move away from the origin to some maximum, and turns out the maximum is right around here. This can be made a little bit more clear by looking at the exact domain in a level curve plot associated with the domain itself. So if we open up, this is a Desmos plot of the domain itself. And if we add in some level curves, this first level curve is 2.001. The next one right here is 2.1, 2.2, 2.3, and so on and so forth. This is 2.8 right here, 2.9, 3.1, 3.2, 3.25. You're seeing very clearly that the mass density is distributing, or getting larger and larger and larger as you move further and further and further out. And it turns out that it actually hits its maximum value at a point that you can solve for directly using the methods from optimization before. So if you use the methods for optimization, you get that the minimum value of this function is right here, which is a blue point at the origin, and the maximum value of this function is right out here at this red point right here. I'm not going to go through that calculation right now because it's a little bit long and it's not really relevant to the discussion today, but it's definitely possible to do using the techniques that we've gone over so far. So the idea is that we want to figure out first what the total mass of this region is for this distributed mass. So what we're seeing here is that the mass density is around 2, or 2 if you're using units of kilogram per meter squared, say. It's about 2 kilograms per meter squared around the origin, and as you move out into the further out into the object, the mass density is getting larger and larger and larger until up here it's a value around 3.25 or a little bit larger than that. The actual value of the maximum you can go through and calculate using the methods from before. So the idea is we want to figure out, using our formula, our double integral formula, how to get the total mass contained in this region. So to do this, we need to set up a double integral. Specifically, it'll be total mass in the region is equal to the double integral over the region of this density function and this region is a non-rectangular region, so we have to be careful with our bounds for integration, but it's the double integral of the function 2 plus x squared plus y squared dy dx. Now what's interesting to note after the last lecture is that very often an integral might be easier to compute if you're integrating over a rotationally symmetric domain. So you might have to use polar coordinates or a different coordinate system to evaluate this integral. It turns out that it's not the easiest way of doing it for this problem, though a good exercise would be to go through and actually do this problem using what we know about polar coordinates. You'll get an integral that will come up to the same value that I'll calculate right now. But I'm going to go through and just do this integral in Cartesian coordinates. That way you can see that. So the idea is that the bounds of this region are going to be for x from 0 to 1. And for y from 0 to 4 times x minus x squared. So this integral is going to go from 0 to 1 for our x bound, and for our y bound it's going to go from 0 to 4 times x minus x squared. So we can do the first integral, or the inner integral with respect to y. Antiderivative of 2 with respect to y is just going to be 2 times y. The antiderivative of x squared with respect to y is going to be x squared times y. And then the antiderivative of y squared with respect to y is going to be y cubed over 3. And this has to be evaluated at the upper bound and the lower bound. So applying the fundamental theorem of calculus here and then plugging in our upper bound and our lower bound. The lower bound is going to be 0, so we don't have to worry about that. And the upper bound is going to be 2. We plug in, we'll get 2 times 4 or 8 times x minus x squared plus x squared times 4 x minus x squared. And then lastly, plus 4 x minus x squared cubed divided by 3. So we have to evaluate this integral with respect to x. It's a single variable integral of a single variable function, but evaluation of this integral will directly lead to us getting the actual mass. The value that we compute is exactly the actual mass contained in this region. So, for instance, if our density function, if its units are being measured in kilograms, say, per meter squared, then the value of this integral, or the mass, will have units of just kilograms. So the main issue with this integral is that it's a little bit long in terms of the algebraic expansion of these terms. So I'm not going to go over the algebra right now of how to simplify this. The main trick here is that you have something cubed, so x minus x squared cubed. So you'll have to expand that cubed term out. All right, you can do that using the FOIL procedure or Pascal's triangle. Right? If you remember from, say, a high school algebra course, maybe, if you compute what's called Pascal's triangle, this gives you the coefficients of different powers of the expression a plus b. So a plus b to the 1, the coefficients of a and b are just 1 and 1. A plus b squared, the coefficients of a and b are going to be, the different powers of a and b are going to be 1, 2, and 1. Right? So a plus b squared is a squared plus 2ab plus b squared. So that the third row in Pascal's triangle give you what the coefficients of a plus b cubed are going to be. It'll be a cubed plus 3a squared times b plus 3ab squared plus b cubed. You can use this trick to get the coefficients for any power of a summation of two variables, but that's what you have to do here with this cubic term to figure out exactly what this simplifies to. But once you go through and you do the algebra on this, it turns out that this simplifies to the following. It's going to simplify to negative 64 over 3 times x to the 6 plus 64 x to the 5th minus 68 x to the 4th plus 76 over 3 x cubed minus 8x squared plus 8x. So this function that we're integrating here, once you simplify it as far as possible in terms of expanding it out in terms of x, right? This is exactly what it simplifies to. And the antiderivative of this is very, very straightforward to go through and get, because we can just go term by term, and we know that this is going to be the same thing as the antiderivative of this is going to be negative 64 over 7 times 3, or 21 times x to the 7th, plus 64 over 6 times x to the 6th, minus 68 over 5 times x to the 5th, plus 76 over 12 times x to the 4th, minus 8 over 3 x cubed, and lastly plus 8 over 2 x squared. This is evaluated at the upper bound of 1 and the lower bound of 0. So plugging into this expression will give us the following calculation, or the following sum. So we plug in 1 here, we'll get negative 64 over 21 times 1 to the 7th, plus 64 over 6 times 1 to the 6th, minus 68 over 5 times 1 to the 5th, plus 76 over 12 times 1 to the 4th, minus 8 thirds times 1 cubed, and then plus 8 over 2, which is times 1 squared, which is just 4. And then when you plug in 0 here to each one of those x values, you get 0. So this number simplifies down when we bring everything to common denominator to the fraction 59 over 35. And if you're using units of kilograms per meter squared, say, this means that the total mass contained in the region with the density function given is 59 over 35 kilograms, or approximately 1.6857 kilograms. So there you have it. You have that if you have this region, this specific lamina, with this specific mass density function, integrating that mass density function over the region will give you the total amount of mass that's contained in that region for that distributed mass density function. So this is a very, very nice procedure that we have, and it's directly applicable to the concept of charge density as well. If instead you have a charge distribution or a distributed charge density function, the double integral of that charge density function will give you the total amount of charge contained in the region. Typically the charge density function could be potentially measured as, or in units of, it's a sigma, as units of, say, it'll be coulombs per meter squared, say. It's the potential units for our charge density function. So that this is the first two applications that we have for the double integral. So for another good example, let's go over and do a charge example. And see how to calculate the total charge on something. And this is the electric charge. So suppose that we have a plate and we want to find the charge. This is the electric charge. An arbitrary segment of a circular plate of radius r. For the density function, This is the charge density function. So it can be negative. Mass density can only be positive. The charge density function, sigma of xy, is equal to x times y times e to the negative x squared plus y squared. And we know what the density plot of this function looks like. We know that a circular plate of radius r is going to look like this. And the charge density is going to be distributed throughout this, where we have a maximum in the first quadrant and the third quadrant, a minimum in the second quadrant and the fourth quadrant. And this is what our plate is going to look like if we do out a density plot of this function. And I will visualize this a little bit later on once we find the exact analytical solution. So an arbitrary segment of this plate is given by the inequality theta between alpha and beta for a minimum angle alpha and a maximum angle beta. So for instance, you consider this arbitrary segment right here, and this is our region R that we're integrating over if we want the charge on this arbitrary segment of the plate that has this charge density function. So what I'll do is I'll call this Q alpha beta to denote that we're dealing with this segment corresponding to angles alpha and beta. And this is going to be the double integral over r alpha beta, where this is the alpha beta segment of this plate of the charge density function. And this is where we really see that all of those helpful techniques for integration become really, really important, because in Cartesian coordinates, this double integral and the bounds of this double integral are relatively complicated. And it's going to immediately pay to be able to just, instead of going through and trying to evaluate this double integral in Cartesian coordinates, immediately switch to polar coordinates to get the value for our answer. And in polar coordinates, x is going to be r cosine of theta, y is going to be r sine theta, and x squared plus y squared is going to be e to the negative r squared, and dy dx or dA is going to be r dr d theta. But the bounds are going to simplify very, very greatly, because the theta bounds are just going to be from alpha to beta, and the r bounds here are going to be from 0 to r, where r is the radius of this plate. This will be the integral from alpha to beta of the integral from 0 to r of r cubed e to the negative r squared times cosine theta sine theta dr d theta. And what's nice here, and this is a little bit of a kind of a trick that sometimes happens, it doesn't always happen, but if your function splits into a product of a function of each one of your variables, in this case we have a function of r here and a function of theta here, well, we know that we can pull the theta function out of the r integral and just integrate the r integral. Because we're integrating from a constant to a constant here, or we're integrating over a rectangular domain in r theta space, right? Because we're going from a constant to a constant to a constant. When we do this, this integral is going to break down to just being the integral from 0 to r of r cubed e to the negative r squared dr multiplied by the integral from alpha to beta of sine of theta times cosine of theta d theta. And what this means then is that our problem of doing a double integral is really just the problem of doing two single variable integrals. You can just go through and do iterated integration here. You'll get the same result. But I just wanted to point this out, that this is sometimes a very important simplification that we can use if we're integrating over constant bounds in our integral for each one of our variables, and the function that we're integrating simplifies to a product of functions. And so if I call this I1 and this I2, and just use some of my techniques from calculus 2, that I2 can be figured out using u substitution. Specifically, if I substitute in u equals sine theta, then du is going to be cosine of theta d theta. So this integral will be the integral from sine of alpha to sine of beta of the function u du, which is just u squared over 2 from the bounds of sine of beta to sine of alpha. And this is going to be sine squared of beta minus sine squared of alpha over 2. And likewise, we can go through and evaluate the integral for I1. This is going to require two steps. First, we use a u substitution. And I don't want you to get confused here. This u down here is not the same thing as this u right here. So maybe I'll use a different variable. I'll do a w substitution of w is equal to r squared. So then dw is going to be equal to 2r dr. And this integral right here will become the integral from 0 to r squared of w times e to the negative w times 1/2 dw, which is the same thing as 1/2 the integral from 0 to r squared of w e to the negative w dw. So this integral is not evaluated yet, but we're getting a little bit closer to what we want, because now we can go through and do a standard integration by parts. And this integration by parts will be when, and this is, I will use u. This is different than the u from the u substitution from before. We'll use u is equal to w. So then du is going to be equal to 1 dw. And then we'll use dv is equal to e to the negative w dw, so that v is going to be equal to negative e to the negative w. And this is integration by parts. So I1, using the integration by parts formula, right, uv from our bounds minus the integral of v du, again from our bounds, this is our standard integration by parts formula. This will become, give us the value negative u times v is going to be negative e to the negative w times w, evaluated from r squared to 0. And the next part is the integral from 0 to r squared of v du, which is going to be the integral from 0 to r squared of negative e to the negative w du is just 1 dw, which is dw. So I1 is equal to negative r squared e to the negative r squared. When you plug in 0 here, you get 0 times e to the 0, which is 0. This becomes plus the integral of e to the negative w, which is going to be negative e to the negative w, evaluated from r squared to 0. This is negative r squared e to the negative r squared. And this will be plus e to the 0 minus e to the negative r squared. Or finally 1 minus 1 plus r squared times e to the negative r squared. This is our value of I1. Oops, and I just realized that I am missing a 1/2 here. I seem to have dropped this 1/2, so I apologize about that. Let's go through and fix that right here so that this is correct. 1/2 here times this entire thing, and then one half times this, and then lastly 1/2 times this right here. So the final value is going to be this entire thing. And I'll just use this line right here divided by 2. So what we've just shown though then is that the charge Q in an arbitrary segment of the plate alpha from alpha to beta in terms of the angle theta is just going to be I1 times I2, which is going to be this value, I1 multiplied by I2. So it'll be 1/4 times 1 minus 1 plus r squared e to the negative r squared times sine squared of beta minus cosine squared of alpha. And you can also use the double angle formula as well to simplify this down to make the sine squareds and cosine squareds go away if you want to rewrite this as well to simplify it a little bit more. But this value is the correct actual value of the charge in an arbitrary segment alpha beta of the plate. And we can test this formula out directly. And we can go through and say, well, let's say we consider just the portion of the plate that's the top portion of the plate. So for alpha equal to 0 and beta equal to pi, or 180. And sure enough, if you directly plug into this formula, the charge q0 comma pi in this segment of the plate, when you plug in pi for beta and 0 for alpha, you're going to get that this value is 0, and so the total charge is 0, which makes a lot of sense when viewing the function itself. And so we see here a picture of this charge distribution, and if we restrict to the top of the plate and then kind of visualize this density as we increase the number of points, kind of fill in the number of points, we're very clearly seeing that in this region, because the function is symmetric, the total amount of positive charge is canceling the total amount of negative charge, which is exactly why we got 0. If instead we were to say focus on the upper right or quadrant 1 segment of this plate, which is this shape, this corresponds to alpha equals 0 and beta is equal to pi over 2, or 90, whereas this was 0 and pi. This one is from 0 to 90. The charge in that segment of the plate is going to be 1/4 1 minus 1 plus r squared times e to the negative r squared cosine of 0 is going to be 1 and sine of 0 is going to be 0. And this is going to be times sine squared of pi over 2 minus sine squared of pi over 2. Or sine squared of 0, sorry. And oops, I'm just realizing here I made another little typo here when I wrote this down. I'm so sorry. This should be sine squared of alpha right here. But anyway, so sine squared of 0 is 0. Sine squared of pi over 2 is 1. And so our answer is going to be 1/4 times 1 minus 1 plus r squared e to the negative r squared for any value of r. So for instance, if r is equal to 3, the total charge in the plate in the segment 0 to pi over 2 will be 1/4 times 1 minus 1 plus 3 squared, which is 9. It'll be 10. And 3 squared is 9 plus 1 is 10. 10 times e to the negative 9. And this value is the value of the charge. If the charge density is in, say, coulombs per meter, that means that this number is going to be the number of coulombs, or the total coulomb charge in units of coulombs of this segment of the plate. And I've shown here a picture of this segment, the top right portion of this plate, and you can very clearly see that as we kind of fill this in, the charge density is really only positive in this region. The blue represents close to a 0 value of charge, and the total accumulation of this function then in this region is going to be positive, which is exactly what we showed when we solved for that exact value, which is very cool.